Okay. So, the general question is the capacity of synapses to store multiple memories. That's the general question that we are addressing. And in order to address this question, we asked perhaps a more specific question, which is, let's say that we have a synapse, we have a set of synapses. There are some rules governing the change in synaptic efficacies, and the question that we'd like to know is where after encoding or trying to encode a large number of memory patterns, will there be a trace in the synaptic efficacies about a memory that was encoded a long time ago? This was the question. And as an interesting detour, we started talking about Markov chains, first order Markov chains. By the way, anyone is taking notes?
Are we in the second round?
Okay, good. So we are talking about, at the detour, we are talking about Markov chains, first order Markov chains. And we were discussing a simpler problem than problem of synapses. This is some kind of random walk in this 4 rooms apartment. We wrote the rules of moving from one room to the other. This was depicted here. And I think we ended class on Thursday by saying that the probability to be in any of the 4 rooms as after n time steps would be m to the power of n times the initial probability distribution, where this matrix M is a matrix that denotes the probabilities of transitions from each room to each room. Questions? So this is where class ended on Thursday, and so some properties of this matrix. So first, it has a name. It has many names. Let me find the names. It's called stochastic matrix, transition matrix, probability matrix, substitution matrix, Markov matrix. It has many names, and it has several properties. So the properties of this matrix M are that one is that all these numbers have to be non-negative, right? These are probabilities, transition probabilities. So Mij is non-negative for every I in J. Another property of this matrix.
0 and 1.
I'm sorry? All columns sum to 1. Why? So sum over I of Mij is equal to 1 for every value of J. And the reason is that, well, these correspond to transitions. So from A, if I'm in state A or in room A, I will either move to room A or to B or to C or to D. So the sum of all these has to be equal to 1. Questions? A Markov chain is called ergodic, or an ergodic chain. A Markov chain is called ergodic chain if it is possible to go from every entry to every entry, from every room to every room, after a sufficiently long time. So it will be called ergodic chain if there exists an n such that Mij is non-negative for every ij. So the idea is that we can move from any room to any room after a certain number of times. Yes?
Isn't it non-negative by definition? I don't
I'm sorry. Ugh. Strictly positive. Another name for ergodic chains is an ergodic Markov chain is also called irreducible. So this is just these are just names. So in our example, is our Markov chain ergodic?
You
What?
want it to go straight directly from one room to the other, or just
No.
start in one room and
There exists an n such that. So is this ergodic? Is this example ergodic? Well, clearly, because we can move from, well, for example, if we want to move from D to B, we can go to DCB, or from D to A, we can go DCA. Okay? What would be an example of a Markov chain that is not not ergodic? What do we need to do here in order for? Which door? Okay, let's say I close this door.
No, it's not. It's still ergodic.
I'm sorry?
the door.
It's still ergodic.
Okay,
The D between C and D.
between C and D. So if we close the door between C and D, if I'm in D, I'll get stuck in D and I will never get out. Or if I'm anywhere else, I will never get back to D. So this would be an example of a matrix or a Markov chain that is not ergodic. Okay, let's go back to the original problem, which is this. So, in order to compute the probability of being in a particular place after n time steps, basically what we need to do is to compute this term, right? Okay, so how are we going to do that? Well, actually, it's not very complicated. So M can be written as sum over all the eigenvalues and eigenvectors of the matrix M, right? So what would be the value of M to the power of N? Well, let's just think about M squared. Eventually we will be interested in M to the power of N. So what would be the value of M squared? Well, this would be equal to sum over I, VIR, lambda I, VLI, sum over J, VJR, lambda J, VJL. Right? Just rewriting it, sum over I and J, VIR, lambda I, VIL, VJR, lambda J, VJL. What can we say about this term, VIL, VJR? This would be equal to delta ij. So this would be equal to sum over ij VIR lambda I delta ij lambda j VJL, which will be equal to sum over I VIR lambda I squared VJL. Sorry, VIL. Similarly, M to the power of N would be just equal to sum over I VIR lambda I to the power of N VIL. So let's see what we can say about about the eigenvalues of M. What can we say about the eigenvalues of M? Can we guess an eigenvalue? Can we guess an eigenvalue for M? Well, we could start with this M.
I guess 1.
I'm sorry?
I guess if there's an eigenvalue, it should be 1. Because there might be a stationary point in which the mark.
Why should there be an eigenvalue 1?
If there's a stationary point, then the probability stays the same after the multiplication of the I start with some probability, initial probability, then after the multiplication we get the same probability.
Okay, no, you're saying that if there is a stationary probability, it implies that MP is equal to P. So if there is a stationary probability, that then M should have one eigenvalue.
Because it's ergodic.
Sorry?
Because it's ergodic.
Well, ergodic is defined this way. We didn't say anything about stationary. the existence of a stationary probability.
But that means that you can get from anywhere to anywhere. So eventually, to obtain the same situation. So after enough multiplication, we'll get more or less the same state.
So the question is, so there are two issues. That it's not exactly the same thing. So one question is if there is a stationary distribution. Second, is it always something that you converge to? And how is it related to the issue of being ergodic? So I'll give you an example where behavior is not, you don't converge to anything. Okay, so let's say that we have our house. I don't remember how it looked like, so I would prefer a new one. Okay, so this would be A, B, C, and D. And you're only allowed to go from A to B. You're only allowed to go from B to C. You're only allowed to go from C to D, and you're only allowed to go from D to A. Now, if you start in A, you go A, B, C, D, A, B, C, D, A, B, C, D. Now, this one has a stationary distribution. Stationary distribution would be to spend 25% of, to be with a probability of 25% in every room. However, you will not necessarily converge to it. Let's say you start with A, then your location after a large number of steps will be one of the rooms in a way that is predictable, and the term that is predictable. So it's kind of, but it's more complicated than that. Okay, so some of you guessed that this matrix may have a one eigenvalue. I'd like to argue that it always has a one eigenvalue, and I will do it by guessing an eigenvector. So consider this eigenvector. Okay, let's consider this eigenvector. So if I multiply it by this one, I get 1 by this one. And this is, well, this would be always true given the fact that the sum of the rows is equal to 1. So every stochastic matrix has at least one eigenvalue that is equal to 1. So So every stochastic matrix has at least one eigenvalue lambda is equal to 1, which corresponds to an eigenvector to VL to a left eigenvector 1, 1, 1. This is a trivial outcome of the fact that the sum of the rows has to be equal to 1. Now I'm going to prove to you that all other eigenvalues are equal or smaller than 1 in the, okay? So I'm going to prove that all other eigenvalues have this property that that they are smaller than 1 in the absolute value. Do you want to think about it for a second? These are the properties. So the proof is pretty simple. So the idea is to use the fact that all entries of the matrix are non-negative. This would be the tool of are non-negative. So let's consider one element. Let's consider one eigenvector and one element in the left eigenvector. So sum over I Mij Vi Vj L is equal to lambda Vj L. This implies that the absolute value of lambda times VIL should be equal to sum over I Mij absolute value of VIL, and this is because this Mij, I'm sorry, this is not true.
Maybe it needs to be J between instead of I.
No, because this is the left.
Sum?
It's the left.
Okay.
It's the left eigen.
Why is that left?
I'm sorry? I'm doing it for the left eigen. That's why it's sum over I.
The eighth element of that,
I'm sorry?
shouldn't be the left, the eighth element of the vector, of V?
On the right side.
Right side?
Yes, sorry. This is sum over I, sorry. Okay, so far so good. So now I'm going to consider, well, there are n elements here. One of them would be the largest. So I will denote it by something, I don't know how to denote it. This would be equal to, this would be smaller than sum over I of Mij, VL, just call it max. So this notation means I'm going to consider all the n elements, and I'm going to take the largest. Okay? Are you with me? No?
I don't understand what is the symbol for each of these steps you did.
Well, I'm just taking the absolute value here, so this would be equal to the absolute value here, and this would be smaller than this sum. I'm taking the absolute value inside. So this has to be smaller than this one. It will be equal if all elements are positive. So this is a sum of, in principle, positive and negative elements. This is sum of only the positive elements. But this term is always positive. So I'm replacing the absolute value of this one with this. Now, here I have n elements. Some of them are larger, some of them are smaller. I'm replacing them with the largest one. That's why you have this smaller, larger or equal to.
The largest meaning the largest norm, so that's
Yeah. Okay. Specifically, this would be true for the one element that is largest. So specifically, specifically true for the one that is largest. Yes?
Vmax is the maximal element in the vector?
The element that has the largest norm in this vector.
Okay. It's not like the whole norm of the vector.
No. This is just the one element that is largest. You have n elements, I'm taking the largest one. Okay. What's the next step? What's the sum over I of Mij? Indeed. So this implies that absolute value of lambda has to be smaller than 1. And in general, if we take a general matrix, general ergodic matrix, then all eigenvalues will be smaller than 1, except for the eigenvalue that corresponds to the left eigenvector 1, 1, 1. Why should we care about it? Why is it interesting?
Because after a long time there will be only one macroscopic state. With
So this would imply that in the limit of n going to infinity of m to the power of n, if all lambda I are smaller than 1 except for 1, then in the limit of n going to infinity, m to the power of n will be equal to what? Lambda I to the power of n will be equal to what? To 0. So we will be left with v1 r, 1 to the power of n, which will be equal to 1, and v1 left. Or p, this is the notation that we had 3 times t is equal to n. This is in the limit of n going to infinity. This would be equal to vr1 times v1 left times p at t0.
what do you mean by subscript 1?
I is equal to 1. So I have n eigenvalues. First one is equal to 1, and the rest are equal to other things. What can we say about v1l times p? What's v1l? Vector of 1s. So what can we say about v1l times p? Okay, let's be explicit about it. So v1l times 1. Why 1?
The sum of all
This is equal to this 1s times this p times t is equal to 0, which is just sum over I of pi at t being equal to 0. Sum over probabilities of all possible states is always 1. So this is equal to 1. So this will be equal to v1r. So this addresses, was it you? This would be the stationary distribution, v1r. Yes?
Shouldn't they be like the left and the right eigenvector will be autonomous to each other? Because maybe I don't remember them that well.
No, you're confusing VL times VR, which is equal to delta IJ. But what we have here is VR times VL. So this is VR, and this would be VL. Okay?
Yeah.
Questions? Okay, so now we know how to compute the stationary distribution for a stochastic matrix. All we need to look for is the right eigenvector which corresponds to eigenvalue 1. That's simple, right? Well, we have a problem here. What will happen if this vector, right eigenvector, corresponds to eigenvalue 1, will have a negative terms in it? How can we interpret it? I mean, who guarantees that this vector will be composed of non-negative elements?
Why do we need it to be composed of non-negative?
Well, because if we argue that that the probability will converge to this term, then it has to be, well, the elements have to be non-negative, right?
And also bounded from above.
I'm sorry?
And also bounded from above. You can fit it out.
Well, that's another problem. I mean, if we have a probability 2, then we have a problem.
Yeah. We said that there is at least one eigenvalue that is 1, but here you said that there is only one. Does it matter?
In general, you'll have only one. But if you generate if you add noise to the stochastic matrix or something like that, but this is not necessarily the case.
It's not affecting this conclusion anyway.
But this will not affect, well, in some sense, yes, because if you have two eigenvectors that correspond to eigenvalue 1, then the result will be more complicated because you'll still be left here with a sum over two elements, and then the solution would be will be determined by the contributions relative to the corresponding eigenvectors. So it turns out that there is a mathematical theorem that is called the Perron-Frobenius, Frobenius theorem that guarantees that all elements would be non-negative. So basically it says that if you have a real square matrix with positive entries, the eigenvector, the right eigenvector that corresponds to the largest eigenvalue will have non-negative elements. This doesn't answer, was it your question about what will happen if the elements are larger than 1, like 2? Okay. So now we are guaranteed that the elements will be non-negative, but can they be 2 or something horrible like that?
Will you write them here?
I'm sorry?
Will you write them here?
I said it again. I will. If you have a real matrix composed of non-negative real values, the right eigenvector that corresponds to the largest eigenvalue will be composed of non-negative elements. So should I say it again?
Yeah, that's actually so.
Okay.
Because that is so.
So we are talking about a matrix that is composed of, to be more precise, it's composed of positive elements. This theorem tells us that the right eigenvector that corresponds to the largest eigenvalue will have a non-negative elements. Actually, I think they should be positive.
That could be non-negative.
No, it would be strictly positive. If the matrix is positive, then they should be strictly positive. The element would be strictly positive. Now, our problem is slightly more complicated because the transition matrix can have 0 elements. But there are extensions of this theorem to guarantee that we will not find ourselves with negative elements in the eigenvector that corresponds to the largest eigenvalue. But still doesn't solve our problem, right? So what's the solution to our problem? It's actually not too complicated. You know what? Let's leave this problem. So just for all of us. So we have an issue here. This theorem guarantees that the element will be non-negative, but it does not guarantee that the element will not be equal to 2 or something horrible like that, which does not correspond to a probability. Let's do an example and then go back to your concern. Okay, so we have a simple example. So the elements are half, half, quarter, 3/4. So this would correspond to a Markov chain with 2 states, A and B. Probability of transition from A to B is 1/2. Probability of staying in A is 1/2. Probability of going from B to A is 1/4, and probability of staying in B is 3/4. So now we're looking for, so we know that there is one eigenvalue that is equal to 1, and the left eigenvector is 1, 1, and the right eigenvector will be the stationary distribution of this Markov chain. So let's find the right eigenvector here. So how are we going to do it? Well, we know that lambda I minus m times, let's write the vector A1 should be equal to 0. And we're interested in the eigenvalue which is equal to 1. So we're interested in solving this equation for half minus quarter minus half quarter times A1, this should be equal to 0.
Wait, how do you know it has to form a
Well, just
guessing?
I'm trying to find A. To be a way of finding A.
How do you know what?
I'm sorry?
You can always normalize that.
Ah, okay.
No, but still, can you explain what it means? What is A1?
This is just the eigenvector. I'm just looking for A. Just a way of finding the eigenvector.
The second eigen.
The right eigenvector that corresponds to eigenvalue 1, because we already know that there exists an eigenvalue 1. Okay. So we know that half A minus quarter is equal to 0, or that A is equal to 1/2, which implies that VR is equal to 1/2 and 1. Right? So this implies that after a long time, the dynamics will converge to this probability half 1. Right?
Not a valid probability.
I'm sorry?
Not a valid probability.
It's not a valid probability. Why is it not a valid probability?
Not sum to one.
Well, it does not sum to 1. Okay.
What do these probabilities belong to? I mean,
So there are two questions. Let's start one by one. So let's follow our logic. So here we prove that the dynamics will converge to the right eigenvector that corresponds to eigenvalue 1. We try to find the right eigenvector that corresponds to eigenvalue 1. A1 is a right eigenvector that corresponds to eigenvalue 1. We look for A. A is 1/2 and 1. And if you plug m times half 1, well, let's see what you get. We will get the half and 1, because here we'll get quarter plus a quarter, which will be 1/2, and here we'll get a quarter plus 3/4, which are 1. So this is a right eigenvector of the matrix M. However, this does not look like a probability distribution because it does not sum to 1. Yes?
why do the elements in the eigenvector have to sum up to 1? Because in the vector of 1, it also doesn't sum up to 1.
Well, because we said that the dynamics probability will converge to this eigenvector. So it certainly will not converge to this eigenvector.
But why would this eigenvector be?
This was the left eigenvector.
So
This is the right eigenvector. We said that it will converge to the right eigenvector. No? Well, we know the left eigenvector is 1, 1, 1. Well, 1, 1 here. Well, we have an issue of normalization because we said that V left times VR is equal to delta Ij. So V left here is 1, 1. So this is it's true that this is a right eigenvector of the matrix M, but this is not normalized such that this is satisfied. So in fact, the dynamics will converge in this example. The probability in the limit of n going to infinity will be 1/3, 2/3. Normalized version of this one. So now going back to your concern. So if all elements are positive and they sum to 1, then none of them can be larger than 1. Okay? Shall we take a break? Any questions? Let's take a break, and after the break we will go back. Well, we still have something about this, and then we'll go back to sinuses. No, this is equal to delta Ij. This is an eigenvalue that corresponds to this is left eigenvector corresponding to one eigenvalue, this is right eigenvector corresponding to another eigenvalue. So the product is delta don't know what delta ij is?
Oh yeah, I just don't remember. I think I
Delta ij is 1 left and right side.
only one state. I think we done it in I just
Right and
What is this vector? What are these options?
okay. When we do okay.
For some B
עדיין אתה יכול לכתוב אותה בצורה הזאת.
מקבל אבל U ו-V שהם לא בהכרח אורתוגונליים אחד לשני, זה לא לך. כי סתם תראה כתרידי לא אפשר לך שתי מטריצות אורתוגונליות. אחד לשנייה. אני גם כן עושה את כל מה שקורה. היא לא סימטרית, לא יודע למה היא כן כנראה שהיא יוצאת לו מבחינה, לא יודע למה.
לא, היא לא חייבת, לא בטוח שחייבת. ושוב, במקרה הכללי, לפעמים שאתה מוסיף רעש, אתה מקבל אותה.
גם מצאת הכללית, גם בדרך כלל
You could probably do everything in the Jordan form if you're forced to.
כשאתה מוסיף רעש, התחום שבהם לא לוקחת, בעולם המטריצות,
אנחנו מניחים שזה מקרה פתוגני ולא
מידה אפס, לא, יש כמובן גם קשר למידה אפס, לא לוחצים.
לא, אבל יש כאן ימונים.
The only thing that defines this matrix is what? What do we know about the matrix? And the Latin. No, before that, the more basic thing was whether you define a matrix.
יכול להיות, כן.
Columns of the matrix. So what's that? What is that? אבל זה רוב המקרים.
לא רוב המקרים. לא רוב המקרים.
לוקחים את זה כרגע כהנחת שישית.
אתן לך דוגמה פשוטה.
ברור שאם זה לא עובד, יש לי אזור אחד ואזור אחר.
בדיוק.
כאילו אנחנו מתחילים כרגע כזה משהו פיזי. This is one, this is the first column.
במקרה הכללי,
it's the first column.
אתה לוקח מטריצה כללית.
What do we know about the matrix? What you just said?
אחרת מה שיהיה לך, יהיה לך שני ערכים עצמיים, יש אחד, ואז יהיה לך בעצם, הפתרון יהיה תלוי בפרוג'קשן של שניהם על פני ההתחלה. ברגע שזה בעצם כמו של חוסר גודל.
From the left of the matrix. It's supposed to be the left side of the multiply it from the left side of the matrix.
Okay.
Take this from the left side of the matrix here.
Okay.
This way.
Okay.
אז לא תזכיר את השטח שלו כחיים אחרים. אני מראה את הפרטים. קטן, כאילו, בסדר גודל של חלק.
לא, לא. כן, אתה יכול גם רק ללחוץ על זה. לא יודע, זה... אתה יכול גם להגדיל את העבודות של מטרים.
כלומר, כן, יש עכשיו סטריפ ואני אוכל למכור לך,
This is the geometry, this is the eigenvector, this is the dimension, right?
אתה רק לוחץ על זה.
Every code comes to one, right? And you see that this is the first column of the left metric, right? Yeah, and we have this one.
אתה יכול למרכז אותם.
אני מפחד יותר מכך, אני לא מפחד זה ספר כזה בין להביא יותר ולדבר בנפרד. זה מה זה מפחד שאתה יודע, תשבו את זה עכשיו כמה ארגזים שלי. מה זה בספר? גם שואל בלב. הם יכולים לשתות.
כן, זה אותו דבר, זה מרכז את הטקסט בעצם.
לא, אתה עדיין עושה.
כאילו, הסביבה של הפלוט שלה היא נועדה למצוא דברים האלה בצורה נוחה, אבל אם זה מסורת,
You still don't know this one, right?
מה שטוב בלקטרון, אתה יכול לשים על זה, בפיגר 5, אז סיבה ככה, אם אתה פתאום שם עוד פיגר,
כל הגז
זה 6, אתה לא צריך לתחזק את זה, יודע לבד, כאילו, הוא עושה לך את כל הדברים לבד, ואתה יכול לעשות את זה כמו ספר.
כאילו 5 מתוכם הולכים לשאר לקרוא, והרגע אחד נשאר
This one.
יש יותר מקוד אחד?
יש כמה. כן.
This one should be like one, right? But this is this.
No, right. Yeah, we usually write this. We usually write this transpose. This is a column. This is a row vector multiplied by the matrix. It gives you another row vector, right? Sum over every single column, and you get one at each different column. So it gives you a row vector.
ענקית שיושבת ממש עלינו ביד, רק יש את זה ממש יש עליי.
אבל זה לא עובד על פארק זה כאילו
לא יודע אתה אוהב את זה יו, אוקיי, כמה סקונות
ויש גם תהליך של במה
מה שקטן מדי?
למרות שבליקס זה לא קורה.
זה אחד העקרונות של שיווק ישיר. איתמר, אני שלחתי לך
ראיתי, יש איזושהי בעיה, איזשהו משהו בעצמי
גדולים, קטנים למטה, גדולים למעלה, כל חדש
זה היה לא פרקס בעברית, לא ברור.
בגלל זה גם עכשיו ביקש מאיתנו מישהו שכן,
אחרי שראיתי את זה,
גם מלפת חברה וזה ישיר וגם להחברה לאורגנית, יש לו זן אחרת. שלחת לך גם PDF?
הכי קל לי אם לא תהיה, זה PDF. גם.
כי בעיקרון אני חושב שזה בוורד, וכאילו הייתי צריך הייתי יכול לשמור את זה מוורד
אנחנו בלימוד, כאילו אנחנו שומרים על מותג. אנחנו לא יכולים לשווק תחת אותו מותג. כן.
יש לי אותם כבר
רוב החקלאים עוברים על זה ישר
אם אני מבינה שרוב התכלול הפרטידס
אין הרבה עבודה, שהיום בפייסבוק
לא מאמין כמה עבודה. אתה לא מאמין כמה דעת? ככה, תראה, ככה אולי קיבלנו פועלים בעולם הבא. קוטפים, זה גם המונח, לדאוג שיש פועלים, לדאוג שהקוטפים שמשפיקים לטפל ולהיפטר מהכל, אז קוטפים, ומעשים עושים, הולכים להפקת של סרטונים, וזהו, לא חושבים על זה, ואנחנו, אני חושב שזה כיף 50% מהאנרגיה זה השימוש.
ועל זה השעות, זה אפשר.
אני עושה בקטנה, ככה פה בפחים.
זה כזה שבחים.
כאילו כתבת.
חשבתי שזה פלטפורמה נוחה.
המסחר זה מקצוע. כאילו, אנחנו עכשיו עושים עבודה של שני שלבים. כאילו, זה הוגן שיש ספרים סיפוריים. זה עבודה ממש קשה.
כן, אבל אני קצת מתעצבן על המרג'ן של הקריטריון הזה.
דברים שהם כאילו אחרים. למשל, העובדה שאתה בא לתת את העבודה איזה גם להסתרים זה שאתה לא יודע מי זה קצת זה מה זה, כאילו שהם משתדלים לא לחלוק מידע.
למה? נכון, כי כל הקטע שלי זה
אבל הדשן והדשן, זה בכלל גבוהים. יש את האקוויזן של גבוהים.
אני לא עבדתי עם זה, לא עבדתי עם וורד, עבדתי עם מלבישה שנשמעות על וורד.
מה שאני אומר, שאם אני אקבל באותו מחיר כמוני,
אבל זה שזה לא כמו הסוטה, זה גם וורד אקוויזן. בדיוק.
זה שהם כאילו אתה בא לאותו ספר בשוק, לא יודע שהם עובד כל כך כאילו יש, אם אתה מפתח ספרים קבועים שאתה יודע שלא יודעים, אבל באמת עובדים על הלקוחות, הם לא יודעים את זה, הם לא אומרים את זה, זה הנרדים, הם מבקשים שיסדרו להם.
אבל בטוח שיש אנשים שצריכים את זה הרבה.
לא, סתם כן, עם התותים זה כאילו
קיצור כן, קצתי תחילת קצת ולא השתמשתי בזה עד אתמול.
יש פה ביוטיוב שזה שקר, כאילו אני מניח שזה שקר, כי אם אין אותו תקן אורגני הוא כנראה לא אורגני. יש איש אורגני זה ממש טוב. זה איתנו בסוף זה שני כאילו...
הייתי תגמין כאילו?
בסדר.
אנחנו מקבלים כל אחד עם ה...
Okay, in the last hour we discussed properties of stochastic matrices. We considered a simple example and discussed the stationary distribution. So this embarrassing issue of normalization, which we overcame. And the bottom line is that the long-term behavior of this element will be determined by the eigenvector that corresponds to the one eigenvalue. So this would be the long-term behavior of the dynamics. So the question is, what's long-term? What determines long-term? How long is long-term? Give me numbers. דבר איתי במספרים.
Long-term maybe might be a time that will be much larger than the time that takes you to make one step.
Numbers. Give me numbers. What's long-term? How can I decide whether 10 time steps is a long-term or 100 or 1,000 or 1,000,000? 1,000? And any problem 1,000? That's like a general number? What's tau? There's no tau here.
take the probability. Totally depends on
You need to take the second largest eigen.
Thank you very much. Thank you. So let's consider this example. Well, let's consider this equation. We have an equation. An equation. Okay? We have an equation here. So what does this equation tell us? It tells us that, we have another one, which is here. The probability to, the distribution over state at time n, t is equal to n, is equal to m to the power of n times p times 0. The whole idea of talking about stationary distribution was we took all these eigenvalues and said, okay, if they are smaller than 1, all of them will become 0, and then we will only be left with one contributing eigenvalue, the one that is equal to 1. The rest are equal to 0, and then we had this trick where the sum over probabilities, this here, the sum over probabilities is 1, and then we are left with a right eigenvector which corresponded to the eigenvalue 1. This is stationary distribution. This is only true if these are small. Lambda to the power of n are small. And what will determine whether lambda to the power of n will be small, all of them? Well, we'll take the second largest one and ask for the second largest one, is this value to the power of n small? This is the meaning of long time in this system. So basically, if we want to know whether this Markov chain will converge to a stationary distribution after some time steps, to answer this question, we will need to ask whether the number of time steps is sufficient such that for all eigenvalues, except for the one that is equal to 1, for all eigenvalues, lambda to the power of n is small. And this will be determined by the value of lambda. So whether it's 10, 100, 1,000, or 1,000,000 will be determined by the value of lambda. And the largest one, that is not equal to 1. Is this point clear? So for this particular problem, all you need to do is compute a second, well, the only other eigenvalue. For the problem that was here and is no longer here, same thing. Compute the 4 eigenvalues, take the largest one, and see whether this eigenvalue to the power of n is sufficiently small. This is this is the meaning of a long time scale in this problem. Okay, so sufficiently small would be the question for how accurate you want to be. This is the meaning of convergence. So the convergence will be exponential with n, because it's to the power. Now, if you want to be 10%, 1%, a tenth of a percent of the stationary distribution, again, you will be able to do it knowing the value of lambda. But this is like an exponential, this is like the tau in an exponential decay. We want to find this tau, but tau will be determined by lambda. I'm sorry? You have
I wanted to suppose maybe that lambda by the power of n should be like 1,000 times smaller than the lambda on the first.
That's a question of taste.
Yeah.
Okay? It can be one, depending on your taste, but whether it will be 1 over 100 or 1 over 1,000 or 1 over 10,000, the effect will be, the difference will be small because it's to the power of n. It's exponential in n. Okay? So now you need all that you need to know in order to go back to the question that really interests us. Who cares about random matrices? We care about neuroscience. You care? I saw you. Okay. It's okay. I mean, nothing to be ashamed of. Okay. So we know all that we need to know about random matrices. And now we go back to the original problem. So let's go back. So we have synapses, and the change as a result of learning, and we use the measure of change, and this measure of change was something like the following: S was equal to 1 over n. S is equal to 1 over n. It would be a number of synapses in the network. Sum of all those that were potentiated. The value minus some average value. Minus the sum of those that were depressed. Wi minus w. And now this average W, we can already understand what it is. What's this average W? How are we going to compute it? Average over what? Average over the stationary distribution. What's the stationary distribution? Stationary distribution is the distribution of efficacies given our particular learning rule and the realization of the rules governing the realization of memory patterns. This is average W. Okay. So now I'm going to, so from here on, we can imagine different rules for changes in synaptic efficacies. But we will consider one rule. And the way of describing the rule will be using the transition matrix. Yes? Yes.
So now we're looking for the average W?
No. We're not looking for the average W. What we're looking for is a measure of the memory trace. So imagine the following thing. Okay, you have like a Halting model or something like that. You have a memory pattern. It made a change to the synapse. It made a change to all synapses. Some were potentiated, some were depressed. So we're going to sum over all that were potentiated and subtract from those the ones that were depressed. And then we keep the identity of these synapses and we go and visit them again and again and again and again and again and see whether this term, what happens to this term. Now what will happen in the Hopfield model to this term? What will happen to this term in the Hopfield model?
0.
Why 0?
Half up and half down.
Well, but we're taking. Okay, let's talk about the Hopfield model. It's a good exercise. So in the Hopfield model, what's the stationary distribution of synapses? Hopfield model plus minus 1 with the probability 1/2, the standard Hopfield model. So what can we say about average W? 0. Let's even say something else. What can we say about the distribution of W? Normal around 0. Around 0. Okay. So.
If P is large.
I'm sorry? Yeah, P is large. Yes, P is large. So P is large. And now what will happen immediately after potentiation, after the single memory pattern? So half of the synapse will be potentiated, and their size will increase by 1 over n. Half of the synapses will be depressed, and their size will decrease by 1 over n. So, for Hopfield, immediately after presentation of a memory pattern, we will have sum over I. How many synapses will be potentiated? Which is how many? N squared over 2 will be potentiated. So S will be equal to 1 over N. How much? What's N? N is 1 over N squared. There are N squared synapses. So this would be S is equal to 1 over N squared. There will be N squared over 2 that will be potentiated by 1 over N, minus N squared that will be depressed by 1 over N. Okay? So together, this will be equal to 1 over N. So this is the magnitude of a change following the presentation of one memory pattern. Sorry?
Plus 1 over N.
Minus 1 over N.
Yes. Thank you.
I'm sorry, I lost you a little bit.
Okay.
Because I don't understand what W means and N shouldn't it be
W is synaptic efficacy.
like Jij?
Yeah. N is the number of small n is the number of synapses in the network. Okay. And basically, in the Hopfield model, half will be potentiated, half will be depressed. Yes.
Can you say again what the average is? What the
Where the average will be 0.
no, not in the Hopfield.
The W.
Yeah.
Where this would be average over the synaptic efficacies. When the average is... I'm sorry?
C equals 0?
No.
Either?
No, this would be at the time in which you're interested in, and we will be interested in a long time. It will become perhaps slightly clearer later. But this is in the Hopfield model. So basically, what can we say about S at a later time in the Hopfield model?
The magnitude of changes will decrease.
I'm sorry?
The magnitude of changes should decrease in time.
The
magnitude of changes, the S should decrease in time until we're done.
No, this is S at time 0. At time, let's say, where 0 is defined as a particular pattern that we're interested in. What will be the value of S at some at a later value?
Is there a threshold?
I'm sorry?
Is there a threshold?
Where I don't have any thresholds in the Hopfield model.
Because once you have too many memories, then you start to get like the probability of error.
But there's no probability of error. There's no dynamics here. I'm only looking at the synapses themselves. Well, S at a later time will be a stochastic variable. It will be normally distributed. Why? Because we start with a value which is 1 over n, and then we add noise to it. But we add noise in the Hopfield model which is unbiased. Some synapses will go up, some synapses will go down. On average, there will not be a change. So we will have the value of S at a later stage will have a mean of 1 over n, but there will be some noise to it. This is what will happen in the Hopfield model. And one way of thinking about capacity here, perhaps, is to say, when will this noise be large enough? Again, it's a nice exercise to do. When will the standard deviation be comparable to this mean. So this is in the Halting model. But remember why we started doing this, why we started this journey in the first place. We said one assumption of the Halting model is that synapses are unbounded, that have an infinite number of possible steps. We were interested in thinking about a problem where the number of states a synapse can attain is finite. So let's think about a slightly different model. And I'm going to define the model. I'm going to define the model using the stochastic matrix. So the way to think about it, well, the way to think about this problem here is that let's continue with the Halting model. So these are the different states that the matrix can attain. So let's say that this is 0. This would be 1 over n. This would be minus 1 over n, and so on. So let's say that at a particular point in time, a particular synapse is in this state. So as a result of encoding another memory pattern, the state of the synapse will change. How will it change? In one of two possible ways. Either the synapse will potentiate, which implies that the state of the synapse will move to this state, or the synapse will depress. And as a result, the state of the synapse will move to this state. So in principle, we can think about the synapses in the Halting model in the framework of the Markov chain, right? No?
No.
Why no?
Because the synapse is unbounded in the Halting model.
Okay, so in principle we can think about it in the framework of Markov chain if we assume that the Markov chain has an infinite number of states. So thinking about the Halting model in this framework is like thinking about a Markov chain with an infinite number of states. Now this is kind of complicated because, for example, we don't know how to compute eigenvalues and eigenvectors of synapses of a matrices that have an infinite number of entries. But in principle, we can think about it this way. So what we are going to do now, all we are going to do is think about a similar framework, but this time using bounded synapses. Something like saying, okay, this is it. This synapse can have, I don't know, 10 different states, or 50 different states, or 100 different states. And we'll have some transitions from one state to the other. And then we can use the tools that we learned here in order to think about the capacity of this model. And when thinking about it this way, we immediately realize that we have a problem. A serious problem. A problem that should lead all of you to start shedding tears. The first one to cry, I will know that he or she understands the problem that we are facing. I'm sorry?
Very large vectors.
What do you mean by large vectors? Vectors of what? What will be this size?
I think we need to find some m that is the stationary probability of changes in the system.
Well,
like
m is a matrix.
Of size n of size n.
Well, this will be we started with an infinite Markov chain, and now we're in a finite Markov chain with a finite number of states. Yes?
Are changes like a normal variable? So maybe it won't always change by 1 over n, but it can change in like a lot of different values?
Well, we can consider different models. I mean, one model would be, if we think about a variant of the Hopfield model, then you will always change by 1 step. You can think about other models where you change by 2 steps or something like that. But independently of the model that we will use, we can think about this as a Markov chain. If we think about this as a Markov chain, I'm sorry? It will converge to a stationary distribution. It will converge to the stationary distribution exponentially fast. It will converge to the stationary distribution exponentially fast. This will be almost independently of the details here. Now, if it will converge to a stationary distribution exponentially fast, then this term, which denotes the difference between those that were potentiated and those that were depressed, will go to 0 exponentially fast. If it will go to 0 exponentially fast, then our ability to store memories will be very limited. I'll say it again. If the distribution, so if we think about this process as a Markov chain, we know that it will converge exponentially fast to a stationary distribution. Converging to a stationary distribution implies that this signal goes to 0. Because all memory on those that were potentiated and those that were depressed will be lost. So this implies that if we think about a finite number of states, the ability to store memories will be lost. So what we will do now is to compute it. We'll consider a particular model and see what's the capacity of this model. So the particular model that we will consider is the following model. And the model is defined by the transition matrix.
This model doesn't have this problem, or it still has?
Which model?
The new one that you're going to introduce.
Well, and the point that I'm trying to make that any model will have this problem.
So why?
Well, I want a number. One thing that I want is a number telling me how bad things are. Second, I want to know how the number of states here may affect the memory capacity. So if I double the number of states, what would be the effect on memory capacity, for example? So the model that I'm going to consider is a model that has this form in which a synapse can either potentiate, depress in one step, or not change. These are the 3 possibilities that I'm going to consider. So the transition matrix will look something like this. So it will be an m by m matrix. There will be m states here. And looking at the diagonal, an element in the diagonal will look something like this. A synapse can either depress or potentiate. Looking at one, so this is the diagonal element, above diagonal and below diagonal. So if I'm in this particular state, I can stay in this state with a probability 1 minus f minus f plus. I can potentiate with a probability of f plus, and I can depress with a probability of f minus. In the Hopfield model, what are the values of f plus and f minus? Half. So in the Hopfield model, the probability of staying is 0. I'm potentiating with a probability of 1/2, and I'm depressing with a probability of f minus. Is it sufficient to describe the model? What's missing? Well, this is the result of the learning rule. So this is the result of the learning rule. So I don't need a learning rule beyond this. All I want to know is, given this, what would be the value of this? Yes?
I don't understand what are the other elements in the...
Okay, so what's the probability of moving in one step from here to here? 0. Is there anything that is missing here?
What about this first and the last?
So what are the boundary conditions? So the question is, what are we going to assume? Let's say that we are here and we're supposed to potentiate. So there are various ways of writing the model. One is using what's known as hard bounds. So hard bounds would mean that potentiation will bring you to the same state, and depression will lead you to this state. So in that case, the diagonal term would be 1 minus f minus here and f minus here, and then 0. So this would be an example of a hard bound case. Another possibility is to use soft bounds. In soft bounds, you will have 1 minus f minus f plus, f minus f plus as before, but here we'll have 1 minus f minus f plus, and here we'll have f minus plus f plus. So the idea in the soft bounds is that whenever I want to potentiate, I depress. So these are two different models that are in the limit of large n, they will behave very similarly. Questions about the models? Do you understand the models?
What is it? This means that the rule is not the same for all synapses? I'm not sure I understand what...
Well, in the Hopfield model, you could always potentiate and you could always depress. Here we are thinking about synapses that are bounded. So the question is what to do with the bound. So as long as you are in the middle, no problem. Potentiate, depress, whatever. But the question, what will happen here, and what will happen here? So we can assume we can consider different models. One model would say that if I'm here and I need to potentiate, then I just don't change. This would be considered a model with hard bounds. This would be a model saying that if you want to potentiate from this state, instead you depress. Now, this seems slightly more plausible, this one. But it turns out that this one is one that can more easily be solved analytically. And in the limit of large m, they will behave similarly. So basically what we need to do is take one of these models There are many zeros here. And what do we need to do with these models in order to answer this question? We need to find the second largest eigenvalue. The second largest eigenvalue will give us a measure of the decay time. What you were saying, what you were considering as 1,000. Okay? So this is what we need to do. We need to take these matrices, or one of these matrices, and compute the eigenvalues, or at least compute the second largest eigenvalue. So I asked Itamar to do that. Actually, this can be done. But he said, "Oh no, I don't want to do it. It's too long, because it will take an hour or two." And so what we will do, we will just post the solution. The reason why it is slightly complicated are these boundary terms. If it wasn't for these boundary terms, this is a Toplitz's matrix, and finding the eigenvalues is easy. These are the Fourier components. But we have this term, we have this thing here in the boundary that make our life somewhat miserable. So, but still, I mean, it's not too difficult. So I will state the eigenvalues, and this can be done for the case of soft bounds. So what will be the first eigenvalue? The largest eigenvalue? 1. This is this has to be, because it's a stochastic matrix. There is another one. I'm going to call it lambda 2, but it's not the second largest. Just because it's different from the others, I'm going to call it lambda 2, which is equal to 1 minus 2 f plus f minus. This is a term that exists here but does not exist here in the hard bounds case. And this is a result of these particular boundary conditions. And we have many other values which have an interesting form.
Lambda 2 can be negative?
Well, f plus f minus, f plus would correspond to the probability of going up, and f minus corresponds to the probability of going down. So we cannot have that the two probabilities be larger than 1. So at most it would be, this will go to -1. Yes. The other terms which we will be interested in will be equal to 1 minus f plus f minus plus 2 square root of f plus f minus. Lambda k is equal to 1 minus 2 f plus f minus plus 2 square root of f plus f minus cosine of k minus 2 pi over m minus 1, and this would be for k being equal to 3 to m. So these are the other eigenvalues. Now this form comes from the Fourier series corresponding to the Toplitz's matrix, and for large M, the subdominant term will be lambda 3 is approximately equal to 1 minus square root of f plus minus square root of f minus square minus square root of f plus f minus pi squared over m squared. This would be for large M. So for large M, the behavior will be dominated by this eigenvalue. So what can we learn from this term? So what are the things that we should care about? Right? One thing that we should care about is the issue of number of states. How much do we gain from adding states? So let's say that we have 50 states. Will moving to 100 states make the capacity much larger? So one thing that you immediately notice is that if M is large and F plus is not equal to F minus, then we have a problem. Then lambda 3 will be dominated by this term. Remember, what we care about is how different we are from 1. So if F plus is not equal to F minus, then lambda 3 will be substantially smaller than 1 independently of the value of M. So this tells us that in this model, we need F plus and F minus to be balanced. So what's F plus and F minus? F plus is a probability of potentiation. F minus is a probability of depression. Now remember, last week we talked about the covariance rule. We spoke about the problem when, in the Hopfield model, when potentiation and depression are not balanced. So this is another way of seeing it in the general case. We need potentiation and depression to be balanced. We need F plus to be equal to F minus in order for the network to be able to store a large number of memory patterns. So this is an important determinant for memory maintenance, that F plus will be approximately equal to F minus.
M here is the number of states, or?
M is the number of states synapse can attain. That's the size of the matrix. Yes?
Why lambda 2 isn't enough?
I'm sorry?
For storing memory? Why lambda 2 is not enough for storing memory? Why do you need lambda 3?
Why? I'm sorry?
I'm asking why do you need F plus and F minus to be balanced if you have lambda 2 who can store the...
How can you store with lambda 2?
Let's say that F plus and F minus are equal to 1 together. So in that case, lambda 2 doesn't, it stays plus minus 1. It gets minus 1, then it doesn't decrease to 0.
Right, then it flips.
So it flips. So if it's close to 1, so it always flips, so that's the reason that you can store anyway, because it's no, but if F plus and F minus are small enough, then lambda 2 is close to 1.
Okay, so the question is, that's actually a very interesting question that you can already ask it here. Okay, so your point is the following. Maybe we can overcome the problem by taking F plus and F minus to be small enough. For example, if we take f plus and f minus to be equal to 0, then we no longer have a problem.
But it will be very boring.
Well, in what sense will it be boring?
You won't have any loss. I don't know, it's like a boring. You all the metrics is
Well, I don't care about being boring. I mean, this is, you can argue about the whole class. All I want to do is store memories.
okay, so take f plus and f minus to be 0.
Okay, so let's take f plus and f minus to be 0. Good idea, but what will be the consequences?
You have to store more memory.
If I take f plus and f minus to be 0, then I can store as many memories as I want, right?
Why? Because all eigenvalues will be 1.
Yes, fantastic. But,
Doesn't it mean that it's static, like the network will
so the network will be static. So S0 will already be equal to 0.
Yeah.
So there's it's not, well, the fact that it's boring is one thing, but more importantly, we'll not be able to, there will be no signal. The signal, even at the first time point, will be equal to 0. But you're raising an important point, which I was hoping to leave under the rug and not talk about it, which is the consequences of playing with f plus and f minus. But now I have no choice, but I will not do it today. I will have to do it on Sunday, but I was, on Thursday, but I was clearly hoping that no one will ask this particular question. But now I'm schooled. Okay, so I'll see you on Thursday.